Okay, welcome back. Today we're going to continue and finish up with Chapter 7. And so today is going to be all about applying the central limit theorem to solve problems when it involves questions regarding the mean of a population, or the mean of a population mu. So we're going to continue on with questions regarding that. So basically today is just going to be examples of problems that involve the use of the central limit theorem to find probabilities of the mean, probabilities related to the mean. Okay, so the mean of a sample, I should say. So here's what we're going to do. So let's start with our first example. And here it says a study involving stress is conducted among the students on a college campus. The stress scores follow a uniform distribution, with the lowest stress score equal to 1 and the highest equal to 5. Using a sample of 75 students, find the probability that the mean stress score for the 75 students is less than 2. Okay, so we know that X, the population, is uniform from 1 to 5. Okay, so that's what we know about the population. We take a sample of 75 students, and they want to know what's the probability that the mean score of the 75 students is less than 2. So that's X bar, right? So the probability that X bar is less than 2. Okay, so now here's a perfect example of where we're going to use the central limit theorem to help us, because what we need to do, and here's the thing you need to always keep in mind, we're talking about the probability of the sample mean, which means we need to know the distribution of the sample mean to answer this question. So again, we want to make sure that the distribution of the sample mean is going to be approximately normal. Okay? And if it is approximately normal, then we'll know what the mean and standard deviation of X bar is. So we have mu of X bar and sigma of X bar. Okay, and we know what those are. Okay, and so remember, mu of X bar is equal to mu, and sigma of X bar is equal to sigma divided by the square root of n. Okay. So the question is X bar normal? And the answer is yes. Why? Because of the central limit theorem. What is the central limit theorem? Remember, it says, hey, if the sample size is big enough, we know that the distribution of X bar, the sampling distribution, will be approximately normal, with a mean of mu and a standard deviation of sigma divided by the square root of n. Well, the criteria is that n has to be at least 30. Well, in this case, n is 75, which is definitely bigger than or equal to 30. So by the central limit theorem, we have it. Okay. So since we know that it's normal, now we can use this information, which again, here it's going to have the same mean. Okay. What's the mean here for the uniform? Well, that's what we need to figure out. Okay. So the mean, if you recall, for a uniform distribution is what? It's the midpoint of the rectangle. So it's a plus b divided by 2. Oh, hold on a second. Yeah. Hold on a second. Why do they have 4 here? That's a typo. So 1 plus 5 divided by 2, which is 3. So the mean is 3. Okay. And the standard deviation, if you remember, the standard deviation for the population of a normal is sigma is equal to b minus a over the square root of 12. So that's going to be 5 minus 1 over the square root of 12. And so what are we going to get for that one? That's going to be approximately 1.155. So 1.155. So we have the mean and standard deviation. So here's an example where if you're given a distribution, you're going to have to use that information for that distribution to find the mean of that population and the standard deviation of the population, just like we did here with uniform. Once you have those two, then you can find the mean and standard deviation for X bar. So in this case, the mean is going to be 3, and the standard deviation is going to be 1.155 divided by the square root of n, which is 75. Okay? Okay. Okay, so that's where we're at now. Okay, so now we've got the distribution of X bar based on the central limit theorem. So which means that now we can use our either the z-table or the calculator to find the probability. So let's use the calculator. It's normal CDF. And so what's the lower bound here? Well, the lower bound here is what? In this case, we're talking about what's the lower bound that X bar could be? Well, it's going to be 1, okay, because that's the lowest here. So 1. And the upper bound is going to be 2. And so then we use the mean and standard deviation, and this is what we're going to use. 3, and then 1.155 divided by the square root of 75. Okay, so then what do we get? Well, let's check the calculator. So we go to the calculator and just plug this into your function for normal CDF. And so here's what we get. So if you put this in your calculator, you get 0. So it's so small that even the calculator just says it's 0. So it's virtually 0 that you'll get an average of less than 2 on this scale based on the sample of 75 students. Okay. So that's the answer. So that's an example of where we would use that. So the next question is regarding a percentile. So this was part A. So part B then says, well, what if we have a percentile? Well, it says, what is the 90th percentile for the mean stress score for the 75 students? So again, n equals 75. So we want the percentile, which means the area to the left. Remember, percentile is less than or equal to, right? The percentage of values that fall equal to or less than that particular value, okay? So the 90th percentile is the probability of being less than or equal to, and that's 0.9. So the probability that X bar is less than or equal to some value, right? That's what we're looking for, right? We're looking for that X value. We know that this is going to be equal to 0.9 because it's a percentile, right? It represents the 90th percentile. So this is what we're looking at right now. So now what we're going to do is, since we're looking for a percentile, we're going to use the function for what? Well, we're going to use inverse norm. Okay. So given this information for mu and sigma, so again, this tells us here that x bar is going to be normally distributed. So the central limit theorem is normally distributed with a mean of 3 and a standard deviation of 1.155 divided by the square root of 75. So I'll put that there. Okay. So now here's the thing. Now we're going the other direction. We're looking for an x value. So inverse norm is the function that will give that to us. Okay, we could use the z table, right? We could do that. But if we're looking for a value, we know that the area to the left, right? This is area to the left. Left of what? Left of whatever the x value is, right? X bar value, I should say. Okay? So this is what we're looking for. So inverse norm will give it to us. So if we look x bar, right? We can use inverse norm to give that to us. And do they use inverse norm? Yes, they do. Okay. So if you use inverse norm, well, the first thing you put in the calculator, if you remember, is the area to the left. Well, there it is, 0.9. So it's going to be 0.9 followed by the mean and standard deviation. So the mean is 3, and the standard deviation, of course, is going to be this divided by the square root of 75. So we're just going to put in 1.155 divided by the square root of 75. And if we use that function, let's see what we get. And we got 3.17. 3.17. So that's the mean. That's the mean score that represents the 90th percentile. So what does it tell us? It says that among all samples of size 75, so if we were able to take all of the samples of size 75, 90% of the mean stress scores are at most 2.3, and that 10% are at least 3.17, and at least 10% are 3.17. Okay, so again, let's think about what this means. It means that if we took all of the possible samples of the same size, in this case 75, and we calculated all of the sample means, then we would say that 90% of those samples would have mean stress scores of less than 3.17. And then 10% would be at least. Okay, I hope that makes sense. So, again, we would expect that of all of the samples of size 75 that we could have, that 90%, because it represents the 90th percentile, right? That 90% of all of those samples will have averages, sample means, that are less than or equal to 3.17. And then at least 10% of those, or excuse me, 10% of those would be at least 3.17. Okay? So that's that question. Okay, so now let's do another question. So now, it says, suppose that a market research analyst for a cell phone company conducts, hold on, let me do this. So it says, suppose that a market research analyst for a cell phone company conducts a study of their customers who exceed the time allowance included on their basic cell phone contract. The analyst finds that for those people who exceed the time included in their basic contract, the excess time used. So we're talking about excess time, the time that they went over, okay? The excess time follows an exponential distribution with a mean of 22 minutes. Consider a random sample of 80 customers who exceed the time allowance included in their basic cell phone contract. Okay, so let's use this as an example. So here we're going to deal with a population that has an exponential distribution. Okay, so we know that X, which is the excess time, right? The time that they went over their contract, follows an exponential distribution with a mean of 22 minutes. So mu equals 22 minutes, which means that the M equals 1 over 22 because it's exponential, right? The decay constant. Okay, and then N, they say consider a sample size of 80, so 80 customers. So we're going to use this information to answer the following question. Okay, so again, X represents the excess time used by one individual cell phone customer who exceeds his contracted time allowance. Okay, so now A says, find the probability that the average or mean excess time used by the 80 customers in the sample is longer than 20 minutes. So A says we want the probability that the average time for these 80 customers, X bar, is longer than 20 minutes. That's what we want to find. Now, again, we need to know what the distribution of X bar is. We know the distribution of X, but that's not going to help us. We need to know the distribution of X bar because that's what the probability is for, okay? We're not talking about a probability about X, we're talking about a probability question for X bar. And since we're talking about the mean, that's what we need to find, okay? So, how do we know? Well, what do we want to know? We want to know that X bar is normally distributed or approximately normally distributed. Now here, the population doesn't give it to us because the population isn't normal, right? If the population is normal, we'd be in like Flynn because the population tells us if the population is normal, then that would automatically give us that the X bar has to be normal. But here, it's not normal, it's exponential. So now we have to use the central limit theorem, okay? So the central limit theorem tells us if our sample size is bigger than what, or at least what? 30. So here, our sample size is 80, definitely bigger than 30. So that's going to tell us, using the central limit theorem, that X bar is approximately normal with a mean of what? Well, what's the mean of the population? Well, mu is 22, okay? So it's going to have the same mean. What about the standard deviation? Well, what's the standard deviation for an exponential distribution? Well, if you recall, but exponential distributions, the mean and the standard deviation are equal. They're always equal. So what are the characteristics of an exponential? So this is also equal to sigma. So sigma is also equal to 22. Okay, so now what do we know? We know that this is going to be the mean because it has to be the same, but the standard deviation of X bar is sigma divided by the square root of n, so sigma is 22 divided by the square root of 80. And so here's our normal distribution for X bar. Now we can use normal CDF and just plug in the values, right? So the first thing is our lower bound. Our lower bound here is what? It's going to be 20 because it's greater than. So we have to start at 20 and it goes up to what? Well, it goes to infinity on the exponential, right? Or on the normal curve. It goes off to infinity. So what we're going to do is we're going to use what? 10 to the 99th power. So 10 to the 99th power, followed by the mean, which is 22, followed by the standard deviation of X bar, which is 22, divided by the square root of 80. And what do we get? Well, well, let me just look in here. We get 0.7919. 0.7919. And that's the answer. Okay? So again, you just need to remember what you're putting into the calculator. Lower bound, upper bound, the mean, and the standard deviation. Okay? Now in this case here, since we're dealing with an exponential, we know that the mean is 22, and in the standard deviation is also equal to 22. And so now that tells us what to put in for the standard, the mean and the standard deviation for x bar, if it's normal. Okay. Now, B says, suppose that one customer who exceeds the time limit for his cell phone contract is randomly selected. Find the probability that this individual customer's excess time is longer than 20 minutes. This is asking for what probability? The probability that x is greater than 20. Well, now what are we talking about here? We're not talking about a sample mean anymore. We're not talking about the sampling distribution anymore. We're talking about the distribution of x, the probability of x, which means we need to know the distribution of x, right? Not x bar now. Well, we do know the distribution of x bar. It's exponential. So now we have to use the formula for finding the probability of an exponential distribution. Okay? So in the formula that we should remember is this one. So this is always equal to e for greater than. Remember, it's greater than. E to the negative m times x. So remember, m is 1 over 22. So all we have to do is just plug in e to the negative 1 over 22 times x. Well, what's x? X is 20 in this case. And so this is going to equal e to the negative 20 over 22. And then all you have to do is just put that in your calculator. And what do you get? You get 0.4029. So 0.4029. Okay, so that should be a recall from chapter 5. Okay. Let's see here. So C. Let's see here. C is. Oh, basically, why are these two different? One of the things that we're looking at here is because they're two different distributions. One of the reasons why they're going to be different is because, one, they're two different distributions. Two, exponential distribution is a skewed distribution versus a symmetric distribution for normal. So you're definitely going to get different probabilities for these, for that reason. Oh, and by the way, they're also involving two different random variables. That's the other thing. This is involving the mean. This is involving x. Well, hence, that's why they have two different distributions, right? So now, let's see here. Okay, so let's do the next question here. So the next one is dealing with the percentile again. So here, it says find the 95th percentile for the mean excess time for samples of 80 customers who exceeded their basic contract time allowances. So again, we're in the same situation, so we know this. And then the next question that we want is going to be, what's the probability, or what's the 90th percentile? So we're looking for a time now. We're looking for the average time that represents the 90th percentile for all samples of size 80. Okay, so we're looking for, we know that the probability that x is less than or equal to some value, right? We're looking for the value, is equal to 0.95 because we know that this value is the 90th or the 95th percentile. Okay, so the fact that we know it's the 95th percentile gives us the probability, right? Because it's the percentage or area to the left, right? So again, we're looking for an x value, right? We're looking for an x bar value, okay? So again, x bar is going to use, since we know it's normal, we're going to use inverse norm. So we're going to use inverse norm. And the first thing we're going to put in is the area to the left, in this case 0.95, followed by the mean, which is 22, followed by the standard deviation, which is 22 divided by the square root of 80. Okay, and then we're done. All we do is just plug it in, and what do we get? We get 26.05. 26.05 minutes. This is the 90th percentile. So again, what does this mean? Well, we're talking about x bar, so what this percentile, what this means is that 90% of all of the samples we could get of size 80. So if we took all of the possible samples of size 80 that we could get from this population, we would expect, we know that 90% of those samples will have a mean time of 26.05 minutes or less. Okay? And then also 5% of those samples will have averages that are greater than this. And that's what it means. Okay? So again, just make sure you understand what these numbers mean. That's really the important part of it. Obviously, it's important to get the correct answer. That's also vital, but understanding what these numbers mean is very important. Okay. Okay. Let's see here. And all of this was done using the central limit theorem, of course, except for the one with x, but we know the population. Okay. Let's see, what else? Let me see here. Okay, let's use this one. Okay, so here's the last one we'll do. Okay, so the last one is, it says, a study was done about violence against prostitutes and the symptoms of the post-traumatic stress that they develop. The age range of the prostitutes was 14 to 61. The mean age was 30.9 years with a standard deviation of 9 years. Okay, so here's what we have. So the ages of the prostitutes, hold on a second. Yeah, here we don't know what the population distribution is. That's fine. It doesn't matter, right? The central limit theorem doesn't take that into consideration, right? So that's irrelevant. So now in this one, so what if we don't know the population? So it's all we know is that the ages, right? The ages, so x equals the age of a prostitute. And we know that the age range is 14 to 61. Okay? We know the range, so the age range is 14 to 61 years. Okay? And what do they tell us? Well, they tell us mu, right? The average is 30.9 years. And the standard deviation for all these, ages is 9 years. Okay? So what do we know? This is what we know, okay, from the problem. Now, it says, in a sample of 25 prostitutes, what is the probability that the average age of the prostitutes is less than 35? Hold on a second here. You know what? They use the central limit theorem here, but I'm not going to do that. Let's change the sample size because we know that a sample size of 25 is not big enough. So we're not going to use that. Let's use 30. Let's use a sample size of 30. So let's use, or 35. So let's say n is 35. Now let's calculate the probability that that the mean age of the prostitutes is less than 35. So of the sample size of 35, let's find the probability that x bar is less than let's do 32. Let's do 32. Why not? So what's the probability that the average age of the sample, right? The average age of a prostitute of the sample of 35 prostitutes, their ages is less than 32. Okay? So now, how are we going to do this? Well, we need to know the distribution of x bar. Well, again, we don't know anything about the population distribution in this case. So we're going to rely on the central limit theorem. So the central limit theorem again tells us if the sample size is bigger than or equal to what? 30. So this is definitely at least 30. So the central limit theorem tells us that x bar is going to be normally distributed with a mean of what? 30.9. And the standard deviation of x bar is what? 9 divided by the square root of 35, the sample size. Okay, so now we have everything we need to know, and since we're dealing with probability and a normal distribution, we're going to use normal CDF. And so what are we going to stick into the calculator? The lower bound is going to be what? Well, in this case here, what could we use for the lower bound of ages of prostitutes? 0. Okay, so we don't have to use negative 10 to the 99th power. So we could just use 0. That makes sense, okay? The upper bound here is 32. And then the mean is going to be 30.9. And the standard deviation is going to be 9 divided by the square root of 35. And then if we stick that in our calculator, what do we get? Well, let's do that. So and we get 0.7652. Okay, so what does this mean again? It means that the probability that a randomly selected sample of 35 prostitutes, the probability that their average age is less than 32 is 0.7652. Or in other words, we would expect that approximately 77% of all of the samples that we would get. Okay, so if we took all of the possible samples of size 35 and we calculated the sample mean for all of those samples, we would expect that approximately 77% of all of those samples would have average ages of less than 32 years of age. That's what it means. Okay, so that's, let's see, that's that question. So now it says, B says, is it likely that the mean age of the sample group could be more than 50 years. So is it likely that the mean age of the sample group could be more than 50 years? Well, in this case, if we calculated the probability of being that much, so we already know that 76% here is less than this. Well, if we calculate, what is the probability? So what is the probability that the average age is greater than 50? Well, we're going to use normal CDF, right? Calculate the probability. So what's the likelihood? That's probability. So normal CDF, we're going to put in again, our lower bound here is going to be 50, right? What's the upper bound? Well, the upper bound, this is where our age range comes in. So in this example, we have an age range. So it's going to be 61, right? So 61, oh, actually, you know what? Oh, let me back up. I did that other one. Oh, I forgot the age ranges in the last one. Hold on. Let me go back. So let me redo that one before. So X bar was what? Less than, what was it? Less than 35. It was less than 32. Less than 32. Okay. So it's less than 32. We forgot the age range. They were 14 was the lowest age. So it's from 14 to 61. So let me redo this one because that is wrong. So normal CDF, and some of you probably caught that, but you can't say anything because it's a video. Okay, but anyway, so normal CDF, right? So normal CDF, here's our probability, here's our range. What's the lower bound? Well, the lower bound is not 0, it's 14. That's the difference. So 14, and the upper bound is 32, and the mean is 30.9, and the standard deviation is 9 divided by the square root of 35. So let's redo that one real quick. So it'll be 0.765. Oh, it's exactly the same. It's exactly the same. 0.76, because it didn't matter, because it already took this into consideration with the standard deviation. So actually, this is a great example of where, because of the distribution that's given to us, that it's based on this age range. So it didn't matter. Remember when I told you guys that in certain circumstances, you can always put in negative 10 to the 99 here for your lower bound, 0. It doesn't change, right? So here's a perfect example where it doesn't matter, okay? Because it's not going to change if you go lower than 14, because that's what the distribution is based on, okay? So again, so it's the same answer, 7652. So never mind. So we get the same answer. So that's actually pretty good. So now let's do the probability that X bar is greater than 50. Okay, so now we're going to do normal CDF. Now the lower bound here is 50, and the upper bound here is 61. And of course, the mean is 30.9, and the standard deviation is 9 divided by the square root of 35. And that becomes a really small, excuse me, a really small number. really, really small number. So basically 35 zeros, a decimal, so 0.35 zeros, and then 192. So very small number, essentially 0. So it's very, very, very unlikely that that would ever occur. Okay, so that's the answer to that question. Now, the 95th percentile, again, we're going to do the next one, the last one, which is now we're dealing with the 95th percentile. It says find the 95th percentile for the mean age of 65 randomly selected prostitutes and interpret. Okay, so let's do that again. So here's the idea. So 95th percentile. So 95th percentile, P95 or the 95th percentile implies what? That the probability that X bar being less than or equal to, remember, percentile, less than or equal to some value, right? Some X value is what? Equal to 0.95. Okay, and now we're looking for an X value. We know that it's normally distributed, so our X bar value that we're looking for is going to be used, we're going to get it by using inverse normal, right? So inverse norm, and what's the area to the left that we put in? Well, 0.95. What's the mean? 30.9. And what's the standard deviation? 9 divided by the square root of 35. And the value that we get is 32.7. Oh, hold on. No. Gotta put in the right numbers. 65. Sorry, guys. This is 65. Okay? So here, n, they changed the 65. So if we took n as 65, well, that's even better. It's still bigger than 30, so we still have everything, but this is now 65. Okay? So now we have this situation here. Okay? So this is still the same, but we're going to stick in 9 divided by the square root of 65 here, and that gives us 32.7. 32.7 years. So again, so interpretation of this means that if we took all samples, all possible samples from this population of size 65, we would find, and we took this sample mean of all of those samples, then we would find that 95% of those samples would have an average of at most 32.7 years. So the average age would be, for each one of those samples, for all of those samples, hold on, let me reset. So 95% of all of those samples would have an average age of, at most, 32.7 years. And then we would find about 5% of those samples would have ages that were greater than 32.7 years. Okay, that's it. So now, let's do one more. So this is the last one. Okay, so here's another example. And in this example here, it says, according to Boeing data, the 757 airliner carries 200 passengers and has doors with a mean height of 72 inches. Assume for a certain population of men, we have a mean of 69 inches and a standard deviation of 2.8 inches. Okay. So here's a population of men. So we're talking about heights of men. And we have, so this is heights of men in a certain area. And the mean height of these men is 69 inches, 69.0 inches, and a standard deviation equal to 2.8 inches. Okay, so that's what we know. It says, A says, what mean doorway height? Okay, so it says the average, so of these airlines, the average door height is 72 inches. Okay? And it says, what mean door height would allow 95% of all men to enter the aircraft without bending? Okay, so here's what they want. They want to know what mean door height would allow 95% of men to enter the aircraft without bending. Okay. So we're looking for a height, an average height of the door. What would the average height of the door need to be in order to allow men from this population to, or 95% of the men in this population to enter the aircraft without having to bend over or to stoop to get in? Okay. So this is a percentile problem because it's, as long as the height of the door, the average height of the door is above a certain height, it'll allow 95% of the men to go into, which means they'll be at that height or less. Okay? So I hope you understand that this is a percentile problem again. So it's going to be that we want to find the 95th percentile of heights of all men, for heights of all men, right? Of this group. So it's going to be the same problem as what we did before. So we want the probability that the average height of men in this area, whatever that height, we want whatever that height is to represent the 95th percentile. So again, we want this to be 0.95 for the area to the left. Okay? So again, we're looking for this value. Okay? So it's going to be a problem. And here's the thing. Since we're looking for a height, right? We're looking at a height of a man, the maximum height of the man, right? It's an inverse problem, right? We're looking for a value. We're not looking for a probability. So in this case here, we're looking for the average height of a man, what they need to be. So that would be inverse norm. And so in this case here, again, we put in the area to the left. In this case, it's going to be 0.95. And then the area, or not the area, the mean. Now here's the thing. We need to know the distribution of x bar, right? We still need to know the distribution of x bar. Well, in this case, the average height of men, or men in general, the heights of men, heights of women, this is normally distributed. So x here is normally distributed with a mean of 69.0 inches and a standard deviation of 2.8 inches. So in this case here, we're using the population. So in this case, the sample size doesn't matter. Okay? So, let me see here. Okay, we're also going to assume that we're using all 200 men. Okay, so N is going to be 200. So 200 people. Okay, we're going to use all men since the average height of men is larger than the average height of women. So if we assume all men, then we'll get everybody into the aircraft. So that's why one of the reasons why they're using men in this case. So in this case, we're going to N is 200. So the central limit theorem also gives it to us here. Even if they didn't tell us this, the central limit theorem also gives it to us, because we can assume that we're dealing with a full craft, right? So in either case, we can assume that x bar is normally distributed. So x bar is normally distributed with a mean of 69.0 inches and a standard deviation of 2.8 divided by the square root of 200. Okay? So this gives it to us because of the central limit theorem, but also we know that the heights of men tend to be normally distributed. Okay? Now the problem doesn't tell us that, but which is fine. In a classroom situation, you would be told that it's normally distributed. So I'm just saying that now. So in this case here, you have it both ways. Okay? Now, in this case here, what are we going to put in? We're going to put in inverse norm. So the area to the left is 0.95. The mean is 69. And the standard deviation is 2.8 divided by the square root of 200. And so what is the height of a man that represents the 95th percentile? It's going to be Sixty-nine point 33. So 69.33 inches. Okay, so again, if we took all possible sample sizes of 200 out of this population,